This is my final year project Symposium. Hi, my name is Ko Chin Hang, and my final year project title is Determination of Adulteration Traces in Petroleum and Diesel by using Optical Fibre Sensor. So before we go to the proposed method, we need to understand the problem. And our problem here obviously is the adulterated petrol and diesel. We all know that this is not a good thing where seller mix the fuel with other adulterants such as kerosene to reduce the price and sell it at a cheaper price, which not just cause damage to your vehicle but also to the human health system and environment at a long-term effect. And you're asking why this is a problem? Because it is hard to detect where it has a physical and chemical property that's similar to the fuel, and also the detection process nowadays are slow and inaccurate. There are some process that accurate, but it's either long-winded or it needs a space-consuming equipment. For example, distillation test. That's why we propose the idea of optical fiber sensor with the objective to optimize the tracing efficiency and speed, and also to test the eligibility of tapered single mode fiber in this detection process. And the last thing is to identify the changes of refractive index in adulterated fuel based on its adulteration percentage. In order to make it work, we need to go through three phases in our methodology, which is design, simulation, and data collection. So we can see from the right hand side here is my flowchart of the process, which we will fabricate the fiber first and then come to some condition, so simulate in different core radius and compare with the adulterated petrol refractive indices sample to get the result at the end. So let's go deeper inside this process. And for tapered fiber design, the fabrication of fiber is done in COMSOL multiphysics, and the simulation of different conditions was done in COMSOL as well. So there are two different design proposed, which is a fiber with cladding and a fiber without cladding. So let us talk about the first one here. In here, there are a core cladding and also an analyte layer, which to simulate that the fiber is already immersed inside the petrol sample. And this is to simulate the normal state of a tapered fiber where the cladding are still exist. And in our second design here, the fiber without cladding only consists of a core and a layer of analyte. This is to simulate the thinner state of tapered fiber, because after using a flame brush to thinner out the fiber, sometimes the cladding is thin enough to be negligible. So that's why there is a proposed design to simulate either is there possible if we simulate it without a cladding. And next here, the core radius is also very varied, where the core radius range from 0.2 micrometer to 1.4 micrometer with a difference of 0.3 micrometer in each section, which means there are 5 cases, which is 0.2, 0.5, 0.8, 1.1 and 1.4. This is to collect more data for the simulation to make sure the accuracy, and also to simulate the actual scenario of tapered fiber fabrication, which we can see at the figure here. So as I said just now, the single mode fiber will be brushed on a flame to make it thinner, so it might be some variation in the core radius, where sometimes you pull a little bit harder and it becomes thinner, or maybe it's just a little lightly pull that not really decrease the core radius here. So to make it more accurate and more close to real life experiment, a core radius variation is done. And summary equation here is our main component of this proposed method, because it is used to determine the dispersion of light in the medium, where our medium here is the adulterated fuse. Since we are using it in tapered single mode fiber, the fused silica thermal coefficient was used, where B1, B2, B3, C1, C2, C3 was stated as shown. And lambda here, we are using 1.55 micrometer, also known as 1550 nanometer, is the optimum situation to reduce losses through attenuation. And for the field sample, different adulteration percentage of the sample was given with different refractive indexes as shown in the table. So the data here was collected through some reference on the other research paper, and also based on some prediction after looking at all those data here. Here is my result. And the diagram below shows the surface electric field of fiber with cladding. So for the understanding purpose, we need to know that the red color region shows the highest wavelength where the main optical light focus at, and the evanescence light wave slowly spreading out until the blue region where there are least light spreading. And throughout the increasing of sample refractive index, the evanescence effect is getting stronger, where you can see the red region are spreading wider as well, because the light have refracted out of the cladding to the sample. So at here we can see the surface electric field of fiber without cladding. The same principle apply here. However, in this case, the light no longer refracted through the cladding. You can see the light directly reflected out to the analyte layer from the core, which create a red dot in the center, while all the other evanescent light are reflected outside. And with the increasing of the sample refractive index, the evanescence of the wave are more aggressive than the fiber with cladding. This is because the non-existence of the cladding no longer trap the lights in the total internal reflection. You can imagine it as you let an excited child leave a long hallway to a free open football field. So this is another result collected throughout the project. Effective refractive index is used to quantify the increase in the wave number caused by the medium, and in this case, is used to detect the changes of refractive index in adulterated field. Looking at the graph at the left side, the fiber with cladding shows a uniform increment of ERI based on core radius and sample refractive index. We can see the core size of 0.2 mm have higher ERI compared to the core size of 1.4 mm. However, in another side, the fiber without cladding shows a different trend, where higher core radius have higher ERI at the lower sample refractive index, but all ERI value converge into a similar value at higher refractive index. This is because the evanescence of light had reached its maximum and the core size no longer controls the refractive index. To make it simpler to understand, normal refractive reflection occurs at the core, and the core size no longer alters the ERI. Based on the result collected throughout the project, we can say that simulation using tapered single-mode fiber with cladding proposed a better result. Refractive index of sample shows significant effects on the effective refractive index as the outputs, which means that this proposed method is actually capable to use in adulteration tracing. However, precaution need to be made on fiber core radius when performing this process, because we saw that the radius can change the result of the ERI. By using this method, we can also make a reference data for comparison, or using this equipment in real-time observation on effective refractive index of adulterated fields. In conclusion, we can say that effective refractive index of adulterated field can be tested with tapered single-mode fiber designed with cladding. This actually proves that our proposed method can increase the testing speed in adulteration trace determination. And by introducing this method in other third world countries, maybe we can stop the adulteration field to flow into field market more oftenly. In future, I hope that there are more commercial materials and equipment can be used, and maybe this method can be studied and improved by the next technology revolution. And that's all of me. Thank you for your attention. Bye.